A swarm of earthquakes just woke back up right in the gap between two of California's most dangerous faults. And this comes at the exact same time scientists have published new research suggesting the risk from this region might be even more complicated than previously understood. Let's get right into exactly where this swarm is happening, what makes it different from a normal earthquake sequence, and what the new research is telling scientists to watch for next. Start with the location, because this specific stretch of ground has a long and well-documented history of exactly this kind of activity. The swarm is centered in and around Brawley, California, inside what seismologists call the Brawley Seismic Zone, a tectonically complex stretch of ground sitting directly between the northern end of the Imperial Fault and the southern end of the San Andreas Fault, just south of the Salton Sea in Southern California's Imperial Valley. This area has documented history of swarming behavior going back decades, with notable previous episodes recorded in 1981, 2012, 2020, and 2021, each involving clusters of earthquakes that behave differently from a typical main shock, followed by a gradually decaying series of aftershocks. That distinction matters enormously for understanding what is actually happening here, and it's worth explaining clearly, because it's genuinely different from how most people picture earthquake activity working. There's a real difference between main shock aftershock sequences and earthquake swarms. In a typical sequence, one large earthquake occurs first, followed by progressively smaller aftershocks that gradually decrease in both frequency and magnitude over time, in a fairly predictable pattern. In a swarm, there's no single obvious main shock, K. Instead, activity clusters together without necessarily decaying the way a normal aftershock sequence would, sometimes producing multiple moderate-sized earthquakes in quick succession, rather than one dominant event followed by a clean taper-off. This most recent round of activity began with an initial magnitude 3.5 earthquake, striking in the afternoon, centered about 2 miles west-southwest of Brawley at a depth of roughly 8.5 to 9 miles. From there, activity escalated quickly, eventually including a magnitude 4.7 earthquake, key, strong enough to trigger California's Shake Alert early warning system. Over the following days, the swarm produced more than 350 small to moderate earthquakes, according to local officials, with the city of Brawley activating its Emergency Operations Center as a precaution, while local police, fire, and regional state partners coordinated their response. That center was later transitioned to virtual monitoring as activity gradually settled, though officials were clear that this reflected reduced intensity rather than any declaration that the sequence had definitively ended. Reports of light shaking during this swarm extended across a genuinely wide area, felt as far north as the Coachella Valley, as far south as Calexico, and reaching into San Diego and across the United States Geological Survey. These earthquakes occurred at relatively shallow depths, primarily ranging between 5 and 10 miles below the surface, and shallow earthquakes tend to be felt more strongly at the surface than deeper ones of the same magnitude, since there is simply less rock and soil between the rupture and anyone standing above it. Officials confirmed no reports of significant damage or injuries throughout this swarm, and any tsunami concerns were specifically ruled out, given the fault mechanics involved. Here's a detail seismologists have found genuinely interesting about this particular swarm, and many of the swarms that have occurred in the Brawley area historically. Rather than aligning directly along either the San Andreas or the Imperial Fault themselves, this activity tends to trend perpendicular to both of those major LT lines. According to experts studying the pattern, that perpendicular orientation suggests there may be additional underlying structure connecting the two faults, essentially a more complex web of smaller fault segments linking these two major systems together beneath the surface, rather than the Brawley seismic zone simply being empty, unstructured ground, sitting passively between two separate, unconnected faults. Now, let's address the question everyone naturally asks whenever a swarm like this occurs so close to the San Andreas Fault specifically. Could this activity trigger something larger on the San Andreas itself? According to experts, WHO have reviewed the swarm's behavior. There is a non-zero chance that seismic activity in this specific area could eventually jump over onto the San Andreas Fault. But that chance has been described as remaining low, based on how this swarm has behaved so far. Seismologists tracking the sequence noted that swarm activity had been gradually decaying since it began, which is generally viewed as a reassuring sign. Even though a low probability of triggering a larger event is never treated as a zero probability, particularly given this specific region's documented history and its position directly between two faults, both capable of producing large, damaging earthquakes on their own. It helps to understand just how seriously the USGS treats even a low but genuinely elevated probability during an active swarm like this one, based on how the agency has communicated to rise during previous comparable episodes in this exact region. During past periods of elevated swarm activity in the Brawley seismic zone, the USGS has explained that in a typical week, there's approximately a 1 in 10,000 chance of a magnitude 7 or larger earthquake occurring on the southernmost San Andreas Fault. During active set-W, arm conditions specifically, that same probability becomes significantly elevated, with the USGS having calculated roughly a 1 in 100 chance of a similarly large earthquake within the following week during comparable prior swarms. That represents a meaningful 100-fold increase over the normal baseline probability, EV. And though a 1 in 100 chance still means the far more likely outcome remains that no such large earthquake occurs at all. This is precisely the kind of nuanced, probabilistic communication seismologists rely on throughout an active swarm, treating elevated risk seriously without overstating what remains, even at its highest point, a relatively unlikely specific outcome. Let's talk about why the southernmost section of the San Andreas Fault specifically carries this kind of long-term concern, independent of any particular swarm. This stretch of the fault is capable of rupturing in magnitude 7 or larger earthquakes. But the last earthquake of that scale on this specific southern section occurred more than 300 years ago. Larger scale ruptures along the San Andreas Fault generally are expected roughly every 200 years on average, and the southern portion specifically has not experienced a major rupture since sometime between 1680 and 1690. That means this section of the fault has now gone considerably longer without releasing accumulated strain than its historical average recurrence interval would suggest, a detail seismologists describe using the word overdue, while being careful to note that overdue in this context describes a statistical pattern rather than a specific imminent prediction. Now let's get into the genuinely new piece of the story, research that adds an entirely different dimension to how scientists think about worst-case scenarios involving the San Andreas Fault. According to a study published in the journal Geo, Sphere by researcher Chris Goldfinger and colleagues, two of the most dangerous fault systems along the entire west coast, the Cascadia subduction zone stretching from northern California up through the Pacific Northwest, and the San Andreas Fault, may be more connected to each other than scientists previously understood. This new research suggests these two enormous fault systems can synchronize, triggering earthquakes within minutes or hours of each other, a rare phenomenon that could dramatically increase the total scale of a major West Coast disaster well beyond what a single fault rupturing on its own would produce. The evidence behind this finding came from an unusual source: sediment layers formed by underwater landslides, examined through drilling conducted off the coast of Oregon. These sediment layers, called turbidites, essentially preserve a physical record of past earthquake shaking, since sufficiently strong shaking triggers underwater landslides that deposit distinctive sediment layers on the seafloor, layers that can later be extracted, dated, and analyzed by researchers studying historical earthquake activity. According to this analysis, researchers found evidence suggesting that a major Cascadia Earth-Q wake could trigger a second separate earthquake on the San Andreas Fault, based on unusual patterns identified within these preserved sediment layers. It's worth being precise about what this research does and does not claim, since the exact timing relationship remains genuinely uncertain even in the study's own conclusions. Exactly how much time might pass between these two linked earthquakes, whether minutes, hours, or something longer, remains in question, according to the researchers themselves. What the study does suggest is that instead of a major West Coast earthquake disaster unfolding as one single massive rupture in one specific location, there's a documented historical pattern suggesting multiple regions, potentially spanning from the Pacific N, northwest, down through California, could be hit by significant earthquakes within a remarkably short window of each other. That effectively turns what might otherwise be understood as a single city or single region disaster into something closer to a multi-city, multi-region event unfolding almost simultaneously. This synchronization research connects to an even more direct and recent story, specifically about San Andreas fault risk, published just days ago. According to that reporting, a new study suggests the risk of what Californians commonly call the big one could be greater than previously believed, raising fresh concerns about the potential for widespread damage, specifically across Southern California, in the exact region sitting closest to this summer's brawly swarm activity. Scientists have described the San Andreas as the longest fault in California, and therefore capable of producing the state's largest possible earthquakes, with a widely referenced simulation ORI, originally developed back in 2008, modeling a magnitude 7.8 rupture along the southern San Andreas, producing nearly 2 full minutes of continuous shaking across the region, an almost unimaginable duration compared with the handful of seconds most people associate with even a significant earthquake. So how should someone living in Southern California, or really anywhere along the broader San Andreas system, actually process all of this information together? A currently decaying earthquake swarm in the Brawley seismic zone, a documented long-term overdue status for the SO. Third-most San Andreas Fault. And brand new research suggesting the San Andreas and Cascadia systems might be capable of triggering each other within a remarkably short window of time. None of these individual pieces of information, taken on their own, translate into a specific, actionable prediction about exactly when or where the next major earthquake will strike. Reliable short-term earthquake prediction simply does not exist anywhere in seismology today, regardless of how much data or how many new research findings scientists have access to. And what this combination of information does provide is a genuinely well-supported case for taking earthquake preparedness seriously as an ongoing practice, rather than a one-time reaction to any single headline-grabbing swarm or study. For anyone living across the broader region touched by these fault systems, from the Imperial Valley up through the Los Angeles Basin, the San Francisco Bay Area, and into the Pacific Northwest, the practical guidance remains consistent regardless of which specific fault or which specific new research paper happens to be generating headlines in any given month. Secure heavy furniture and top-heavy shelving that could tip over during strong shaking. Know how to shut off your home's gas line. Keep a stocked emergency kit with water, food, a flashlight, and a battery-powered radio, since power and cellular networks are of 10 among the first services disrupted after a significant earthquake. Familiarize yourself with the Shake Alert early warning system, already active across California and increasingly available in parts of Oregon and Washington, which can provide a genuinely useful few seconds of advance notice before shaking actually arrives at your specific location. Exactly the kind of warning already demonstrated during the summer's magnitude 4.7 Brawley event. And take official guidance from your local emergency management agency seriously during any active SW. ARM, understanding that elevated probability during a swarm, even when it remains a relatively low absolute number, represents a genuine and measurable increase in short-term risk compared with an ordinary week. It helps to understand a bit more about why the Brawley seismic zone specifically behaves so differently from a typical stretch of fault, since that context explains why swarms keep recurring here decade after decade. This region sits within what geologists call a stepover, a zone where the strike-slip motion of the Imperial Fault to the south does not directly connect to the strike-slip motion of the San Andreas Fault to the north in one clean, continuous line. Instead, the plate boundary motion has to transfer between these two fault systems across a more complex zone of smaller interconnected faults, so many of which remain only partially mapped even today. This kind of stepover structure tends to produce exactly the kind of pull-apart tectonic environment associated with swarming behavior, since the crust in this specific area is being stretched and fractured in multiple directions simultaneously rather than sliding cleanly along one single well-defined fault plane. That same stepover structure is also part of why this specific area sits so close to young volcanic features like the Salton Buttes, a group of small rhyolite lava domes that last erupted roughly 9,000 years ago, since the same crust stretching that produces earthquake swarms here also allows heat, and occasionally magma, to rise more easily toward the surface compared with surrounding areas. Looking back at the documented history of Brawley area swarms helps put this summer's activity into useful perspective. The 1981 Westmoreland swarm included a magnitude 5.8 earthquake, while the 2012 Brawley swarm produced a magnitude 5.5 event, both notably larger than the peak magnitude 4.7 recorded during this year's activity so far. A more recent swarm beginning in September of 2020, also in the same general area, produced over 60 magnitude 3 or larger earthquakes across just its first several days, with USGS forecasters noting at the time that past swarms in the region had typically remained active anywhere from 1 to 20 days, averaging around a week in total duration before settling back down to background levels. That historical pattern gives useful context for how this year's swarm might be expected to behave. The USGS has also been consistent in noting that a swarm settling down does not mean the underlying elevated risk from either the San Andreas or Imperial Fault has fully returned to its normal baseline level, since aftershock and swarm forecasting inherently deals in probabilities and ranges rather than guaranteed outcomes. It's worth taking a moment on why this particular research matters beyond just this one swarm, because it reframes a question seismologists have wrestled with for a long time. What does the actual worst-case West Coast earthquake scenario look like? For years, planning efforts for a major San Andreas rupture and planning efforts for a major Cascadia rupture have largely proceeded as separate exercises, treating them as two independent low-probability, high-consequence events that happen to share a coastline. If Goldfinger's turbidite evidence holds up under further scrutiny, and more research is already underway to test it, that separation may not be the right way to think about the risk going forward. A scenario where a Cascadia rupture triggers a San Andreas rupture within hours would mean emergency responders. Mutual aid networks and federal disaster resources that might otherwise be concentrated on one region could instead be needed simultaneously in two or more regions hundreds of miles apart. That has real implications for how states and federal agencies think about resource stockpiling, mutual aid agreements between California, Oregon, and Washington, and how quickly outside help could realistically arrive if the usual assumption that a disaster in one region can draw on undamaged resources from a neighboring region turns out not to hold during a synchronized event. It's also worth being clear about the limits of the turbidite method itself, because that's part of being straight about what this research can and cannot tell us. Turbidites are an indirect proxy for shaking, not a direct earthquake record the way a seismometer produces. Researchers have to infer that a given sediment layer represents a specific earthquake, or a specific pair of near simultaneous earthquakes, based on the layer's characteristics, its dating, and comparisons across multiple drill sites. That inference process is rigorous, but it's still an inference built on incomplete physical evidence from events that happened centuries or millennia in the past, which is exactly why the researchers themselves are careful to describe the timing relationship as an open question rather than a settled fact. Good science reporting means holding on to that nuance rather than rounding it up into a more dramatic, more certain-sounding claim than the study itself supports. There's a broader pattern worth naming here too, because the Brawley swarm and the Goldfinger research are really two different scales of the same underlying story. At the small scale, you have a specific, well-instrumented zone that seismologists have watched closely for decades, where the behavior is genuinely well characterized. Swarms come, they cluster, they mostly decay, and the historical record gives real, useful context for how the current one is likely to unfold. At the large scale, you have a much newer and much less settled question about how entire fault systems separated by hundreds of miles might interact with each other over timescales of minutes to hours. Both of these are legitimate, serious areas of seismological research, but they operate on completely different levels of confidence. Conflating them, treating a swarm recast with decades of calibrated data behind it. The same way you'd treat a single new turbidite study whose central claim is still being tested, is exactly the kind of thing that turns careful science into an overstated headline. Keeping those two threads separate in your own head is part of processing this story responsibly. It's worth spending a little more time on what elevated risk actually means in practical terms during an active swarm, because the phrase can sound alarming without a person really understanding how it changes about their day. A jump from a 1 in 10,000 weekly chance to a 1 in 100 weekly chance of a magnitude 7 or larger event is a genuine, meaningful increase. A 100-fold change is not a rounding error. But it's also worth sitting with what that number means in absolute t-erms. Even at that elevated level, 99 times out of 100, the week passes without a magnitude 7 event occurring. Seismologists communicate this deliberately in relative and absolute terms together because either framing on its own can mislead, say only 100-fold increase, and people reasonably assume a major earthquake is now likely. Say only 99% chance nothing happens, and people reasonably assume the elevated risk isn't worth thinking about at all. The honest picture sits in between those two framings, and that's exactly why officials keep repeating both numbers together rather than picking whichever one makes for a cleaner sentence. This is also a good moment to talk about what overdue does and doesn't mean when seismologists apply it to a fault like the southern San Andreas, because it's one of the most consistently misunderstood words in this entire field. A recurrence interval, the roughly 200-year average gap between major ruptures on this section of fault, is an average calculated from a limited historical and paleoseismic record, not a countdown timer with a fixed endpoint. Faults don't rupture on a schedule the way a train arrives at a station. Some intervals in the historical record run shorter than the average, some run longer, and the underlying physical process, stress slowly accumulating, ulating until it exceeds the friction holding the fault locked, doesn't care how many years have passed since the last event, in a way that makes rupture more mechanically certain just because more time has gone by. What overdue actually communicates is that, statistically, this sektigattasing on a fault has already accumulated more stored strain than the average past rupture has required for release, which is a meaningful data point feeding into probability calculations, not a guarantee that release is imminent. Seismologists use the word because it's genuinely informative, not because they're implying an earthquake is now certain or even especially likely in any given week. For people living in the region, all of this ultimately funnels down to the same practical question. Given genuine uncertainty that will never fully resolve, what's actually worth doing right now? The answer seismologists consistently give is not wait for more certainty before acting. Because in this field, that certainty is never coming. Short-term earthquake prediction, pinning down a specific date, location and magnitude with useful lead time, remain scientifically impossible with current understanding and instrumentation, and there's no serious research program anywhere suggesting that's about to change. What has improved dramatically and continues to improve is probabilistic forecasting, understanding which faults carry elevated risk, by how much and for how long, which is exactly the kind of information this summer's swarm and this new synchronization search both contribute to. That's a fundamentally different kind of knowledge than prediction, and it points toward a fundamentally different kind of response. Not evacuation orders based on a forecast, but sustained, unglamorous preparedness that doesn't depend on getting the timing right. One more piece worth understanding is how this swarm and this research actually reach the people making decisions on the ground, because the science doesn't translate into action automatically. Local emergency operations centers, like the one Brawley activated, don't wait for certainty either. They operate on the same probabilistic logic the USGS communicates, treating 100-fold elevated risk as worth a precautionary activation, even while ignoring that the far more likely outcome is that nothing happens. That's not overreaction. It's exactly how emergency management is supposed to work under uncertainty. Calibrate the response to the actual current probability, scale it up when the numbers say the risk has genuinely increased, and scale it back down without ski, declaring victory once the data supports that the immediate elevated window has passed. The same logic applies at the individual level. You don't need a specific date to justify checking your gas shutoff valve, restocking a water supply, or agreeing on a family meeting point if phones go down. Those actions make sense regardless of whether this particular swarm produces anything further, because the underlying fault system they're a hedge against isn't going anywhere. Let's bring this all together. A swarm of earthquakes has reawakened in the Brawley seismic zone, the tectonically complex stretch of ground sitting between the southern San Andreas Fault and the northern Imperial Fault, an area with a well-documented decades-long history of exactly this kind of clustered, unpredictably decaying seismic activity. This summer's swarm included a magnitude 4.7 earthquake strong enough to trigger California's Shake Alert system, and more than 350 total earthquakes, prompting Brawley's emergence by Operations Center to activate as a precaution before transitioning to lighter virtual monitoring as the sequence gradually decayed. And while experts describe the chance of this specific swarm triggering a larger rupture on the San Andreas Fault itself as low, that probability is never treated as zero, particularly given the southernmost San Andreas Fault's well-documented, statistically overdue status for a major rupture. Layered on top of this active local swarm is brand new research suggesting the San Andreas Fault and the distant Cascadia subduction zone may be capable of synchronizing, triggering major earthquakes within minutes to hours of each other. A finding that could meaningfully reshape how scientists and emergency planners think about worst-case West Coast earthquake scenarios going forward, transforming the traditional picture of a single catastrophic rupture into the possibility of multiple major earthquakes striking different regions in rapid succession. The ground beneath Southern California rarely sits perfectly still, and this summer has given scientists genuinely new reasons to keep watching this specific stretch of it more closely than ever. None of what's outlined here amounts to a specful IC prediction of when or where the next major earthquake will strike, because that kind of prediction doesn't exist in seismology. What it amounts to is a clear current reason to treat ordinary earthquake preparedness, the go bag, the secured furniture, the known evacuation routes, the family communication plan, as something worth actually doing now rather than something to think about only after the next headline.